Hello, vintage computer friends, and welcome back on my YouTube channel. Today again we have the Kosmos CP1 computer system from 1984 on the bench, and I want to wrap up what I had started in previous episodes about this machine on my channel. And in one of the last episodes we were implementing a recursive program on this machine, which is challenging in itself because natively it doesn't really offer a stack. And you need something like a stack in order to implement a recursive algorithm. But as we discussed and saw, there are ways around it. You can actually implement a stack yourself by hand using indirect addressing of this von Neumann machine, and that's what we did. But it was, of course, kind of a very simple recursive algorithm. All it did was it was summing up the first n natural numbers in a recursive fashion, right? So basically like factorial, but instead of multiplying the numbers together, it would simply add them, right? And that worked, and it also worked to a certain basically maximum depths, because this is limited by the amount of memory that this machine had, how large the stack can grow, right? And but overall that was working pretty well. And then I actually set out and tried to implement something a little bit more interesting, like the Towers of Hanoi, right? It's a very nice textbook example that really illustrates how recursive algorithms shine, how they can be much more understandable and concise and elegant than iterative versions of algorithms. And I set out to do this on this machine, but then I ran into memory problems. So the machine simply didn't have enough memory in order to fit in the Towers of Hanoi. And yeah, so I had to go to Germany to my storage facility where I still keep some of my stuff and some old machines, right? And I brought back with me the CP3, which is the memory expansion for this machine. So with the CP3, this machine has now 256 words of memory. And again, remember, it's a von Neumann machine, so this memory is used to store instructions as well as data. And it's a decimal machine language, no hexadecimal, right, as you can already see from the keyboard here. And this is what this machine uses. So, and with 256 words of memory, right, we have more than enough space now in order to really implement the recursive version of the Towers of Hanoi. And that's what I want to do with you today. And I'm not going into all the details of the machine language again, which we covered in previous episodes, but I'm walking through the program with you, and then we see what tricks I have used in order to implement a stack, and so on. Yeah, and so in order to not have to type all this in again, because it takes about, like 20 minutes to type all that in, I also brought back the CP2. The CP2 is the cassette interface, and you see I've already set it up here, and it's ready to load the program from tape now. And yeah, on a side note, I had a very difficult time to get this cassette interface to work with the machine. I usually also use a digital voice recorder, right, such as this Philips one here, and that works perfectly for many vintage machines with cassette storage, and it uses PCM, not MP3, right, so it's a lossless audio format, which is of course better than MP3. And I had no success with that, right? No matter how I tried, I could not get it to load back the data from tape. So it was able to record it, right? But then it wasn't able to load the data back. And then I also tried my very nice new old stock General Electric computer program data recorder, which also usually works fine with other machines. For example, with the TRS-80 Model 1, I'm using it, right? And it also offers tone control and volume and all the usual things, of course, you have to do in order to make that work. It's usually fiddle with those until you find the right volume level and the right tone level, right? And none of this worked either. So at that point I was pretty desperate already, and yeah, I actually started, recapping the interface. So you see it here. So I actually replaced all the electrolytic capacitors. Then it still wouldn't work, right? Then I also started replacing the chips. There is an op amp, and those are like NAND and just logical gates here. I also replaced those. All to no avail, right? And at that point I was really ready to give up. And then I said, okay, let's one more try, right? Let's use this Panasonic program recorder that I also have. And what do you know? With that one, it works 100% reliably out of the box, no problems whatsoever. So, okay, but let me load the program now, right? So I'm hitting the cal, I guess, cassette load button here, right? And this bucket basically, this is supposed to indicate a bucket where, data is being filled into the bucket now, right? So let's start our program recorder and let's load back the program here. Actually, I should wait basically until the header signal is there. So now I can hit load. And so when the data is streaming in, you will see that this LED will start to flicker. Hopefully this is going to happen in a bit. And then it takes actually 7.5 minutes to load back the full memory, 256 words. And I think the machine is internally using 2 bytes per word. So it's basically half a kilobyte, 512 bytes on cassette, for which it needs 7.5 minutes then. And you see it's a serial protocol here, right? So I measured this, so it amounts to, I think, about 24-25 baud. So we are not going to wait 7.5 minutes here now, but I'm just going to pause the video now, and then we are going to be back when the program has been loaded, right? Until then. Alright guys, 7.5 minutes later, we were lucky, no read errors from tape. We have the Hanoi program in memory now, and it's ready to run. And I've set up our play field here on the right. We are using 3 packs and 3 disks, right? And we are numbering the packs. The names of the packs are 1, 2, and 3. And remember that in the other versions for the other machines, like the microprocessor as well as the Bush Microtronic, I used hex digits for this, right? A, B, C. And that would distinguish it nicely in the presentation on the display from the disk numbers, right? So something like move disk 1 from A to B, right? So you can clearly see this on the display, right? And you know what a disk is, disk name 1, 2, 3, and what a pack name is, ABC. And the CP1 is a decimal only machine, right? So we don't have hex digits, and so we have to present the information all in decimal, right? And that is of course a little bit challenging now, because, and I also complained about this in my deep dive video, you don't have full control over the display. But given that you can only output opcodes or numbers from 0 to 255, right? You cannot basically output arbitrary content on the display. So for example, there's no way of printing a number 888123 or so on the display, right? You can print 00000 or 11111, right? Because those are valid opcodes and opcode and data, right? But you cannot print anything larger than 255 here, and you cannot print anything larger than 23 here, or was it 24? I forgot. But anyhow, you get the point. So let me just start the program and run it. And then you see what I mean, right? It's pretty clear then. So let me set the program counter to address 0. And I think at some point I said programs always have to start at address 1. This is wrong, right? So you can actually have your program start at address 0, no problem. And then we hit run, right? And again, we are playing with 3 disks, and I put a fair amount of delay in the output so we can move the disks along by hand as the program runs. So this is the first separator now that indicates a new move instruction. And now this is disk 1. And now comes the pack name from 1 to destination pack 3. Okay. separator, next move instruction, right? Disk number 2 from, we are at 1, right? 1, yes, to destination pack 2, alright. Yeah, separator. And now disk number 1 from 3 to 2, I guess. Yep. Separator, and now we are moving disk number 3 from 1 to 3, I suppose, because that's the only valid move. 1 to 3. There you go. Okay. Separator, next move instruction. Move disk number 1 from 2 to 1. Alright. Not much work left. We only need to move disk number 2 from 2 to 3, I suppose. Correct. And now move disk number 1 from 1 to 3, and we're done. Okay, good. So now that we saw the Hanoi program in action running on the CP1, let's see if we can implement it together. But before doing so, it might be good if we reminded ourselves of the recursive definition. So here's again the Pascal or Algol-like recursive definition of the move tower function, which has 4 arguments, right? The disk number, and then the source, destination, and spare pack number, or the names of the packs, 1, 2, 3. And it's of course pretty simple. So if we only have one disk, right, this equals 0 here as the base case, right, then in order to move the tower consisting of that one disk basically from source to destination is you simply do that, right? You just move that disk, right? So like this. And but else, I mean, you have a more complex problem, right? You need to divide and conquer, and that means solve the problem basically by breaking it into parts. So the first breaking it into parts part is to just solve the problem for one disk less, right? Disk minus 1, and then move that tower, right, of one disk less. Instead of move it from source to destination, move it to the spare, right? But you may use the destination as a spare instead. So if I do this, right, then it means I can move 1 here from source to the spare, right, which is 2. And then we return from, we have solved the problem for one disk less. And then we can move the disk, right? So from source to destination from 1 to 3. And then all we have to do is, solve the problem, the 1 minus 1 smaller problem, by moving the sub tower from a spare to where we moved it to destination, right? From 2 to 3. And then we will have solved the problem. So yeah, this is how that works. And just a quick reminder. And usually in order to implement recursion, you need something like a stack. Now, the CP1 doesn't really have a stack, but it offers something that comes close to it, and this is called indirect addressing, right? And so, I mean, a stack is usually, it's just a region in memory, basically, right? And with a stack, usually you have a pointer associated, which is called the stack pointer, right? And the stack pointer is basically just another memory cell, which basically has an address, right? So this address here, basically, this cell contains an address which then points to this address, to this cell. And this then contains the actual value, right? For example, 1. Now, if you want to put another value on the stack, all you do is you increment your stack pointer by 1, right? So now it points to this cell. So if this was, say, address 123, now you are at address 124, right? And now you can actually put something in here, right? And this way, by incrementing the stack pointer, you basically push values on the stack. And the CP1 supports this basically by allowing you to set aside a memory cell to contain an address, which is basically the pointer, right? And then it has two instructions that allow you to refer to this address. Say this is the stack pointer is at address 100, right? So really what you want to do is you want to dereference the stack pointer, right? So you address this stack pointer using its address 100, but then you want to actually write or read values from the address on the stack to which it is pointing to. And for this we are using the indirect addressing instructions of the CP1. In particular, now I forgot the opcodes, there is the instruction 20, right, which does the following, right? 20 is store indirectly. So basically you give it an address, right, of the stack pointer, for example 100, and what 20 does, or AIS, right, store indirectly, is it fetches the address from this stack pointer address 100. It finds 200 here, right? And actually I should say that it's 123. So it finds the address 123 and it goes to the address and then it fetches the value or stores into the cell which it finds there, right? So AIS stores, and 19 is a load operation, and 19 is LIA. So those are the two operations that we are using in order to deal with the stack. For loading over the stack pointer we use 19 and then the stack pointer address, and for storing into the stack over the stack pointer we use 20, and again we give the stack pointer address. Okay, so let's see how we set up the stack here. Basically we are setting up a value stack for source, destination and spare. And that means we need 3 stack pointers, right? So the idea is that with each new incarnation of this move tower, we have 3 variables here. And this is called a stack frame, right? With each recursive call, we are allocating 1 more stack frame, which then has the values of source, destination and spare. And those are being shuffled around, right? And for example like this, and we have stack pointers that point to them, that way we can address them, right? And the stack pointers are being incremented or decremented. Simply, these are the pop and push and pop operations. We simply add 3 or subtract 3, and that way we can keep track of our source, spare and destination values for the move tower recursive function. So you will say, okay, but what about disk, right? And for disk, we can actually do a bit of an optimization. We don't need to allocate space on the value stack in the stack frame for disk, but we can simply maintain this as a single memory cell and simply subtract 1, and when we do the recursive call, right, and add 1 after we returned. So this is a very simple operation, and that makes the memory footprint a little bit smaller. So for disk we are not putting it on the stack, but we simply maintain a register in memory, a single memory cell that keeps track of the current disk number. But for the return stack we also need a stack, right? And so we have 4 stack pointers then, and those are at these addresses here. So we have the source stack pointer at 146, spare at 147, at 148 we have the destination stack pointer, and then the return stack pointer at 149. And the disk number, as I said, we are not putting on the stack, but we are having a single memory cell here at 145, which is not a pointer, but which contains the value directly, right? So, and then we also need a couple of auxiliary memory cells as variables, just to store stuff, right? And yeah, so the stack then starts at address 200 for the value stack until 239, and at 240 until 255 we have the return stack. Okay, so now let's actually look at the program. We are now good to go through it. The first thing is we need to initialize all these stack pointers. And that means we have to say, okay, the source stack pointer needs to contain the start address of the source stack, right? And so I said the stack starts at address 200, and then this is what we load in the accumulator here, and we store this into the source stack pointer, right, at address 146. And we do the same for the spare stack. It starts at address 201, and the stack pointer is at 147. And 202 and 148 is then for the destination stack. Good. And finally, we also need to set up the return stack. So the return stack starts at address 240, and the return stack pointer itself is at address 149. So now we have stored 240 into 149, right? So the return stack pointer has been initialized. All the stack pointers have now been initialized, but now we still need to put values onto the into the stack frames itself, right? And I said for the disk number, here 3, right? We are not using a stack, but we are putting it directly into the disk number variable, right, at address 145. But for the source, spare, and destination variables, we are going over the stack pointers now. So 1 is the pack name of the source pack, and we are loading 1 into the accumulator here, and then we are now using this indirect store over the stack pointer, right? At 146 is the source stack pointer, and that now means basically fetch the address at that location, dereference the stack pointer, right? And at that point in the game, the address in memory cell 146 is 200, right? So it fetches the address 200 and stores the number in the accumulator into that address then, right? So we dereference the stack pointer now and put 1 onto the first, into the first value stack frame for the source variable. And the same we are doing for spare and destination. Okay, now we have initialized the stack pointers, and we've also initialized the first value stack frame with 1, 2, and 3. And we have put in the disk number into the disk number variable in the memory. Now all we need to do is, we are almost good to make the main call now, but we still need to set up the return address. And the return address here for after the main call, when this executed, is address 19, right? And that simply contains a halt instruction at address 19. So we are dereferencing the return stack pointer and putting now the address 19 onto the return stack, right? So when we return now, and this is the main function call to move tower, right? When we return from the main call to move tower, the return stack is popped, and we are returning to this address here, address 19, which is a simple halt instruction. Good, so we made the main call now, right, to move tower, and the process is going now, has been started. And so like in the Algol or Pascal-like definition of move tower, first thing is to check now, do we have the base case, right? And we are not using 0 here, but we are using 1. So we are loading now from the disk number variable the current value into the accumulator, and then, oops, that was 1 too much. And then we check if it's 1, right? So this is the compare opcode, and 150 is a memory cell which contains 1 as a constant. So we are comparing now if the accumulator is 1, and if so, then we have the bottom case, and the bottom case is handled from address 57 on. But if not, then we are in the recursive case, right, in the inductive case of the recursion, and now we need to make the two move tower with 1 disk less calls, and in between the move disk, right? So, and yeah, so we now need to basically set up a new stack frame, right? So we have to make a new recursive call now. And so the first thing we do is we are basically saving now the current values of our local variables into some auxiliary variables, right? So basically disk source, source destination and spare we are getting from the current stack frame, right? But we want to save those into auxiliary variables so that we can easily access them, because we are now going to manipulate the stack and create a new stack frame for the recursive call, right? And we need to have access to these the current values of these variables. So we are simply calling a save and push subroutine here, which basically creates a new value stack frame for these three variables, right? Let's have a look at that. It's not complicated. The save and push is here. So at address 98 it starts. So all it does is it also subtracts 1 now from the disk number, right? So it loads the disk number and then it subtracts 1. 150 is again the memory cell with a 1 constant. 08 is subtraction and stores it back there, right? So this is the n-1 argument is already computed for the recursive call. Disk equals disk minus 1. And now we are getting actually the current values of source, destination and spare by dereferencing the source, destination and spare stack pointers, right? This is load indirectly over the stack pointer, right? So this is the source stack pointer. And we are loading from the address which is kept at that stack pointer location the value at that address, right, from the stack frame. And we are then storing it into our auxiliary variable at 140. We are doing the same for the spare stack value and for the destination stack value. And we are storing all those into aux1, aux2, aux3 merely so we can just, access them later more easily. And now we are good to create a new stack frame. And for that, what we have to do is basically increment all the stack pointers by 3, right? Because the stack frame contains 3 memory cells, right, for source, destination and spare. So in order to make space for a new stack frame, I need to add 3 to all these addresses. That's what I'm doing here. So I'm loading the address now, the stack pointer address, into the accumulator, and then I'm adding 3, and then I'm storing it back. And I'm doing the same for all 3 stack pointers. And also I have to add 1 to the return stack pointer now, so I'm also making space basically for a new return stack frame. And this is all what this subroutine does, right? So it basically saved the current values into the aux registers of the current stack frame. Then it created a new stack frame, both for the value as well as for the return stack. And then it now does a simple return here basically, using this simple return help register. Okay, so we returned from save and push and we are now at address 26 here. So as I just explained, save and push decremented the disk number already by 1 for the next recursive call, and it also created a new value and a new return stack frame for the next recursive call. So we are almost good to make that recursive call, but we still need to fill the new stack frames now with reasonable values, right? And given that we saved the old values of the current stack frame into the aux variables in save and push, we can now load them back from the aux variables and simply dereference the new stack pointers, which now point into the new stack frame, and put the old values, copy them over into the right positions into the new stack frame, right? And so if you look at the algorithm definition here, you see that for this call, source equals source, but destination should be spare and spare should be destination, right? So source remains, but destination and spare are going to be swapped. So that means we loaded source into aux1, and this is at address 140, right? And then we the new source stack pointer points into the new stack frame, to the new source variable, right? And we can simply dereference that pointer and store the old source value into the new source stack frame value. But for the destination stack pointer, we are now not using aux2, but we are using aux3, right? So 142 instead of 141 into the destination stack frame variable. And for the likewise for the spare stack pointer, we are then using the other aux variable. Good. And yeah, now we also need to fill in the return address, push that onto the return stack, right? And we are making the call at address 43, so we will return to address 35, right? So we load the accumulator with the continuation address 35, and then we dereference the new return stack pointer, right, and put that onto the return stack. So, and then we make the recursive call again to move tower, right? So this is just a jump to address 20, which is where, of course, here move tower starts, right? Actually, this page here, right? At address 20. Good. So we made our first recursive call, and now when we return from that call, right? Now we at address 34. When we return from that call at address 35, we actually have to restore the old stack, right? And for this, we need to decrement basically the 3 stack pointers by 3, subtract 3 from each of them, so we have some point back to the previous stack frame. And the same for the return stack pointer, we need to subtract 1. So it points back to the previous return stack frame, right? And for this, we also have created a subroutine here, which analog to save and push, I'm now calling pop and restore. So pop and restore, it also adds 1 back to the disk number, right? Remember that we subtracted 1 in save and push. And from the disk number, and now given that we are not using the value stack for the disk number but the simple disk number register here, the memory cell, we can also simply add 1 back now after we return from the recursive call. That way we are maintaining the disk number simply by decrementing and incrementing this single memory cell, this variable, without having to go over the stack, right? And then we also need to add 3 now. We need to subtract 3 from all the 3 stack pointers and subtract 1 from the return stack pointer. So they are now pointing back to their previous frames, right? Okay, so we are now at address 38, right? And we just returned from the call to pop and restore. And pop and restore was the inverse of save and push. So we restored the value and the return stack to the state they were before we made the recursive call, right? So we are now exactly in the same state as we were when we first entered this level of the move tower function, that level of the incarnation, right? And we can now continue basically with the original values restored, the original disk number, the original source, destination, and spare pointers and values in the frame are restored. And we are now ready to make the move call, right? So because we are looking at the Pascal or algorithm definition, again, we are now in the middle of the, in between the 2 recursive calls, and we simply have to output the move disk instruction on the display, right? So this is happening now at page 4. And for this, again, I have a subroutine here, simple subroutine. Again, we are not using the return stack in order to jump into that and return from that, because there is no nesting of jumps. So we can use a simple return register again. So the routine move one disk is being called, and we simply set up the return address here at address 38 to be 41, right? So this is where we want to continue. Then we store the return address 41 into the simple return address register, and then we make the call move one disk is at address 61. Alright, so let's have a look at move one disk. So this is responsible for producing the output on the display, and it's again using a subroutine to print something on the display. And remember that we need to print these separators between values, right? So that you can actually see that two ones presented in sequence on the display are actually two ones and not only one one, right? Because we will print it as 1 and then 0, 0, 0, 0, 0 and then 1 again. So this is why we have this routine here, disp, basically, which outputs the current accumulator value to the display, but also puts in that separator on the screen. And for this I need to set up calls basically to this simple display subroutine, and then I'm loading that separator 1 1 1 1 1, if you remember from the demo, right? That indicated the output of a new move instruction on the display. I'm loading this into the accumulator, and then I'm calling the display routine, which puts it on the display. So, and when we then return, the next thing we put on the display is now the disk number, right? So we are then calling the display routine for the current disk number, so it outputs the disk number on the display, right? And when that returns, it actually shows the source destination from where the disk is being moved, right? By dereferencing the source stack pointer, right? So it goes into the source, into the value stack frame, to the source variable there, and grabs the value from there, puts it into the accumulator, and then outputs this. And now we are at address 73, right? And now we do the same with the destination pack, right? Also by going over the destination stack pointer into the value stack frame, into the destination variable there, and putting that into the accumulator, right? Load indirectly over the stack pointer, right? So this is how this display routine works, simply by dereferencing the source and destination stack pointers, and loading the disk number as well as the separator, and then calling a disp subroutine which puts it on the display, right? And this subroutine is shown here, right? But all it does is it uses the show accumulator value on display opcode, right? And then a couple of delays basically, and then it returns to the to the caller using again a simple return register. And so we then returned from move one disk, right? So we are actually at address 41 now. So, and now I mean we put the move disk instruction on the display, and now we need to make the second recursive call, right? And I'm not going into detail again here, because that's just the same as for the first recursive call, right? So we did the move disk now, and now here's the second recursive call. And all we have to do is shuffle, of course, the aux variables around a little bit differently this time, but the mechanics are exactly the same as for the first recursive call, right? Okay, so we made the second recursive call by jumping to address 20 where move tower starts, right? And after we return from the second recursive call, we have to restore the stacks now to their previous state, right? So we are using the pop and restore subroutine again here, again using the simple return register 1 here. And that adds 1 again to the disk number, which has been decremented by 1 for the recursive call. It returns the value stack as well as the return stack to their previous state, and then all that's left to do after this is at address 56 is to basically return from the function, right? So if you look at the algorithm definition here, of course, there's nothing here, right? But here's a return basically, and even though that doesn't indicate any action here, of course something has to happen, right? And we already popped and restored the stack, but now we actually need to execute and jump onto the to the address which is now top of the return stack, right? And I haven't shown you yet how to do this. So we actually have a special subroutine again here, which is the so-called return block. So here's the return block. So it starts at address 136. All it does, it dereferences the return stack pointer. So it gets the top of the return stack, the current return address on top of the return stack into the accumulator now, right? And now ideally we would want to indirectly load this and jump indirectly into this, right? But that's not possible. So rather we have to use now one of our aux registers, or the simple return register, to store the address which we have loaded by dereferencing the return stack pointer, stores this into this auxiliary memory location, and then we can execute 21, right? Which means jump to the address which is stored at that memory location, right? So this is how the return to the top of the to the address on the top of the return stack is implemented on the CP1. Yeah, so that's basically it. I think now we have covered everything, and I know that only 0.001% of the watchers of that video are still with me, but remember that I'm mostly doing that for myself, so I'm more than happy if you stayed that long with me, but if not, I totally understand. Alright guys, thanks so much for watching, and I know that's a little bit tedious and technical, but I appreciate you, and until next time, take care, bye.